We just finished 10.2. Now let's go over to 10.3. We are still on the difference of means, but this time the focus is upon the independence. Basically, we are in this kind of situation. We have two populations, they are independent of one another, and we have two population means, mu1 and mu2. Let's subtract one from the other and take the difference, which we call mu delta. By the way, the Greek letter delta is usually reserved for the difference, not just in this course, but everywhere. Now, what is the best point estimate of a population mean? That's a sample mean. So the best point estimate of the difference of population means will be, of course, the difference of sample means, x1 bar minus x2 bar, which we name as xd bar. That was easy to understand, the point estimate part. Now, a little bit trickier part is the standard error part. It turns out that they follow the following identity, which kind of resembles the Pythagorean identity. SE squared is equal to SE1 squared plus SE2 squared. As a matter of fact, this one kind of looks like hypotenuse squared. As a matter of fact, indeed, this is Pythagorean if you dig deeper. But this is just 1000 level course, so I'm not going to go too deeply into that. But in any case, this is Pythagorean. Now take the square root of both sides, and this is what we get. The standard error of the entire system is equal to square root of SE1 squared plus SE2 squared. Now, how do we calculate this SE and SE2? Well, the standard error is the standard deviation over square root of n. So we do exactly the same thing for the first sample, like this, and again for the second sample, like this. In the end, we have this kind of expression, but unless you're really good at algebraic manipulation, you don't have to pay too much attention to that. Let's do an exercise here. The heights of 20 randomly selected women and 30 randomly selected men were independently obtained, and we have this kind of result. So how do we find out the standard errors? Well, standard error for men, let's do female first, it's on top. 2.18 over square root of 20 is what you're gonna get. By the way, this should be approximation because everything is approximation here. And then how about the standard error for men? It's going to be 1.92, the standard deviation, over square root of 30. The sample size, square root of 30, excuse me, sorry about the typo. Okay, you calculate these and you're going to get the standard error for female and male respectively. And then if you put these two together using, well, this formula down here, here I have to replace this one by female and that one for male, and that's it. Run your calculator, you're going to get the standard error of the system. As a matter of fact, let me show you. Here are the computations, and then put those results in place of the first standard error and the second standard error. You end up with 0.600 something. Oh, by the way, the best point estimate is the difference of means. Turns out the difference was 6 inches. Okay, so much for the point estimate and the standard error. One more topic to go before going over to an application problem, that is the degree of freedom. Our textbook author cuts some corner and tells you a kind of shortcut method, which is not really good, that take the smaller degree of freedom, n1 minus 1 or n2 minus 1. But this is not really good. It's not completely wrong, but it gives you an answer which is not very good. This is much better way. Also, it's tougher because, well, just look at this formula. It's more complicated. But it's not too bad because you know what SE1 is, you know what SE2 is, and you know the degrees of freedom. So you have all these values, so all you have to do is just substitute everything and run your calculator. This should not be too difficult, even though it can be tedious. Make sure you round it down to the nearest integer. Well, let's go ahead with an example problem. In this kind of situation, let's find out 95% confidence interval. In order to find out the confidence interval, we have to look up the t-table. For that purpose, we need the degree of freedom. Well, here's a visualization. And at this moment, please do not pay too much attention to these numbers. Numbers I mean by degree of freedom is 37, and the answer 4.78 and 7.21 kind of thing. This is based upon a better solution. Okay, how do we do that? Well, the observed mean difference is 6 inches, so that goes right in the middle. Okay, and here are standard error computations for male and female respectively. Put those two together, then you have the standard error of the entire system. If you're a little bit more comfortable with the algebraic manipulation than the others, then you can use this kind of argument too. But most of the students will probably prefer this one. Now here's a textbook's way, which is simpler, but this is not very good. We simply take the degree of freedom as 19 because for female 19, for male 29, so we simply take the smaller. Then what we get? Well, look up this t-table. We want 95% confidence interval, so we want 2.5% to the right hand side. And for degree of freedom 19, we have 2.093. We need plus or minus 2.093 because we need shading in the left hand side as well. Let's go back to this picture. 2.5% here, also 2.5% in the left hand side as well. So solving this equation, you get x equals to 4.74, 7.26, kind of like that. And that's how you get the confidence interval. But this confidence interval is not very good because this degree of freedom is too low. We can do better than this. Here's a better solution, but let's copy and paste this thing down here. Okay, that's for the textbook method. And here's better solution. This time you use the degree of freedom formula that I gave you. And this is a bit tedious computation, but not really hard because this is just a substitution. Run your calculator after substituting and you're gonna get 37.2 something. You get the degree of freedom of 37 after rounding down. So using that degree of freedom, which is much higher than 19, you get much smaller t-score. Consequently, you end up with this equation, and minus center over standard error is this new t-score. And solving this equation, you get 4.78 and 7.22, kind of like that. And we end up with this confidence interval, which happens to be the same as this confidence interval given by this Mathematicus computation. Now, which is better? Certainly this highlighted one and this presented one is better because this is smaller than the textbook's confidence interval. Same confidence level, 95%, but textbook gave us larger confidence interval, consequently larger margin of error. You see the radius of the confidence interval is margin of error, so this one has bigger error than the other method. So textbook's method works out to a certain degree, but not very well. So it's going to be much better if you use the new degree of freedom formula that was presented here. Right here. Okay, next let's go over to a hypothesis testing example. And it kind of goes like this. Age and gender difference in single-step recovery. Older people are less agile, so if they lean on too much, they cannot recover, so they have to take a step. And younger women, in this case, are more agile, so as you can see, you have bigger figure. Older women have these figures. Those are measures in degrees. And here's a question. Do the above data suggest that true average maximum lean angle for older female is more than 10 degrees smaller? So explicitly this problem asked us to compare 10 degrees. So that's going to be our null value. State and test the relevant hypotheses. And well, here we go. To be a little bit more precise, I have to use mu delta because we are measuring the difference between one and the other. And that too, mu delta, just nitpicking. The problem explicitly gave us 10 degrees, so that's the null hypothesis. So alternative hypothesis is more than 10 degrees. Or actually significantly more than 10 degrees. Sorry about the typo, I forgot the letter E. Okay, now that we have this hypothesis, we have this initial picture. We have this t-graph around null value of 10 degrees, and we have to find out the critical number. Are we doing this for alpha equal to 0.05? Yes, okay. So this red area is 0.05 and consequently this blue area is 99.5% or 95%, excuse me. And you can look up appropriate t-table, to find out t-score for this situation. But in order to do that, we have to find out appropriate sample statistics, which can be a little bit tedious, but here they are. Just add up all those numbers and then calculate the means for younger women and older women, subtract one from the other, and this is observed difference, 14.5. We can also calculate the standard deviations for younger and older women, and calculate the standard error accordingly. We can also calculate the degree of freedom. Again, the same formula, just plug in all those numbers and run your calculator. So we have degree of freedom of 5 and standard error of 2.167 and an observed difference of 14.5. We're all set. Let's go over to this technical step. And here is the t-score computation. End minus center over standard error is the t-score. So end minus center, which is 10, over standard error we just calculated, is 2.015. 2.015, where is it coming from? In the t-table. And degree of freedom is 5 after we calculated using their formula. And then for 5% there we have 2.015. That's how we get this 2.015 from the t-table. Solving this equality, you get x value equal to 14.4, 14.3669, kind of like that, which is a little bit less than 14.5. So where does the 14.5 belong? It's in the red interval here. Consequently, the alternative hypothesis wins, like this. We reject null and accept alternative hypothesis. Yes, the difference is likely to be bigger than 10.